This video is going to start looking at a new functional group, aldehydes and ketones. Let's look at the structures between the two types. Formaldehyde is the simplest aldehyde. It's often used in reactions, but in general the class of aldehydes and ketones have your carbonyl group. Aldehydes have one R group, usually a carbon. The other bond will be to a hydrogen. A ketone, on the other hand, will usually be in two different R groups. Noted here R, R prime. They can be the same R group. They can both be carbons. They can be carbon chains of different lengths. So make sure you're okay to recognize which group you're looking at, because they will undergo similar reactions, but naming will be different. For nomenclature, aldehydes, we think about how alkanes end with ANE sound. We're going to replace that E with an AL, and that's going to be your number one position. So here we have a 4-carbon chain, so that would be butane. We're going to replace that E ending with an AL, so it would be butanal. Our 3 position was where the chlorine is. Again, you're starting at number 1 because your aldehyde is your new higher priority. For this one, it's also a butanal. Here we have a 3-methyl. Here, it doesn't matter which way we go from naming, because either way we're going to have an aldehyde on the end. Ketones, on the other hand, go from E to -one, so ketone, you can recognize them pretty easily. If you have a cyclic ring, you're going to have a oxygen on the number 1 position, so you don't need to name where that is, just like with alcohols. So here, since we only have 4 carbons, and for it to be a ketone, we also don't need to name these positions. Here, example, we could have ketones on different positions, and going from left to right would give you the same order. So this one would be 2,4-pentane dione. The reactions that aldehydes and ketones undergo are unique in that we haven't seen anything like this before. Why are these reactions so favorable? If we think about the bond between carbon and oxygen, we know that oxygen is holding on to those electrons more, meaning that we have not a full carbocation, but enough positive charge on this carbon to make it electrophilic, meaning a nucleophile with a lone pair negative charge will be able to attack at that carbon, pushing electrons out onto the oxygen. Notice the arrows on the oxygen means that that partial negative charge would become a full negative charge. So the incentive for these reactions depends on who's happier with the negative charge, the nucleophile or the oxygen. So it's the partial positive charge on the carbon that is the incentive for this attack. Before we get into reactions, let's think about reactivity. Aldehydes are going to be more reactive than ketones, and this happens because of 2 main arguments. When we think about carbocation stability, we know that the more substituted a carbon is, the more stable it's going to be. So if we know that in the CO bond that it's creating a positive charge or a partial positive charge on the carbon, having 2 carbon groups, R prime versus an R and an hydrogen, is going to be more preferred. So there's going to be a great old partial positive charge on carbon because it doesn't have 2 carbons to help stabilize that positive charge. The other argument we can think of is about sterics, right? So if we have a hydrogen or 2 hydrogens, it's going to be really easy for that nucleophile to get in there, versus if we have a carbon-carbon or even a more branched system. So you actually see ketones with larger R groups because it's going to be harder for that nucleophile to attack that electrophilic carbon, being less reactive. For reactivity, for a lot of carbonyls, you're going to see this same first step in all their mechanisms. We know that that carbon's partial positive, so our nucleophile is going to come in. In addition, we need to see the arrow pushing the electrons out from carbon onto oxygen. Your next intermediate should look like this, where we now have created a new bond between C and Z, and a negative charge has been placed on the oxygen. At this point, with aldehydes and ketones, that R prime group is not a good leaving group. This will change when we get into carboxylic acid derivatives. If Z prime is a strong nucleophile, it does not want to get that negative charge back, and O minus is left to just pick up a hydrogen from acid workup. So you can see here we've turned our carbonyl into an alcohol. In these groups, and this is going to be important moving forward, you can never see a carbon with a negative charge being kicked out as a leaving group or an H- kicked out as a leaving group. So no alkyl or hydride groups can leave. So instead, this mechanism is going to be nucleophilic addition, which is very similar to what we saw with alkenes. The first reaction we're going to talk about is known as a Grignard reaction. It's actually going to place a magnesium in between a carbon-halogen bond. You do not need to know how this happens, but what you do need to see is that once magnesium is there, you're essentially treating it as the carbon has a negative charge. We haven't seen this before, and let's talk about why this carbon gets a negative charge. We've always seen carbon paired with atoms that are more electronegative, making carbon positive. In this case, it's being paired with a magnesium, which is less electronegative than carbon, meaning magnesium forcibly gives his electrons up to carbon, giving it its negative charge. This is often the nucleophile of choice dealing with carbonyl compounds, specifically ketones and aldehydes. But the reason why is because this is an easy way to make new carbon-carbon bonds. So you should be looking at these as carb anions, and here is a quick mechanism or a quick synthesis where our magnesium would come in between the bromine. If we were to give any proton source, that C- would pick off a proton from water and now become CH2. These are going to be strong bases, and you must realize that if you have water around, and in addition to another nucleophile, they are going to act as a base before they can act as a nucleophile. Let's talk about mechanisms. You're going to show your bond between your carbon source and your magnesium as being your nucleophile, pushing into your carbonyl group, pushing electrons out onto the oxygen. We will talk about reactions with lots of different types of functional groups with these, so it's really important to get these arrows down. Once that happens, you'll have your negative charge on your oxygen. Remember, what's the incentive for this reaction? We're trading essentially a negative charge on a carbon for a negative charge on an oxygen. Usually Grignards will always follow up with an acid workup step, and that's just to provide a hydrogen for your oxygen anion. So you always see that if you need to provide reagents, make sure you add that as a second step, or understand what that hydrogen is doing. It's just providing an extra source. This cannot be done at the same time because it would allow the Grignard to react with the acid as well. All of these reagents here, I'm giving you examples with a formaldehyde, aldehyde, and a ketone. All of these arrows would be the exact same, right? That doesn't mean we'd be left with the same type of alcohol. So if we had a formaldehyde, after acid workup, we would get a primary alcohol. If we had an aldehyde, we would have a secondary, and if we have a ketone, we'll end up with a tertiary. So it's important to associate, since all these mechanisms are the same, what functional group are you starting with, what functional group are you ending with. Here's an example of what you would see as a predicting products. Here you're starting with an aldehyde. Your carbon source here, remember the bond between carbon and magnesium is essentially a carb anion. That is your nucleophile. Your product here would be an alcohol at that carbonyl position. So keep in mind too, as far as stereochemistry goes, we did not have a stereocenter. Now we do have a stereocenter, meaning we would have a racemic mixture with both R and S enantiomers.